Hi guys, welcome back to Data Every Day. Today we're going to do a bit of a simple video. I'm just going to do a standard pre-processing with model selection on a data set of e-commerce shipping data. So we have a bunch of different shipments, and you can see each one is for a different customer, and there's 11,000 examples. So I'm not sure if this is synthetic data, but in any case, interesting. It might be real, but in any case, we have a column at the end, which is 1 or 0 depending on whether the shipment reached its destination on time or not. So this is what we're going to try to predict. You can see we may have a slight class imbalance, nothing too bad. So let's see how this goes. Let's hop into the notebook. We're going to use NumPy and pandas for working with the data. For pre-processing, we're going to use the train test split function and standard scalar from sklearn. And then we're going to train a whole bunch of classification models and compare the results. So we have logistic regression, k-nearest neighbors, decision tree, two support vector machines, one with a linear kernel, one without, or with a nonlinear kernel. Then we have a neural network and our ensemble methods, which are random forest, gradient boosting, XGBoost, LightGBM, and catboost. So let's go ahead and import all of that, and we can load in the data using pandas.read.csv. Let me just zoom in and grab the file path for the CSV file up here, and we'll paste that in, and we can take a look. Alright, so here's the data set. We only have 12 columns, so we do have a nice amount of training data to train on. So let's get a little more information with data.info. And we can see here there are no missing values. We have the total number of non-null entries in every column, which makes our job easier. So we'll start pre-processing, and I'm going to create a function called preprocess_inputs. We pass in a data frame, we'll make a copy of the data frame, and for now it will just return the data frame. And I'll store the result of the function in x and pass in data. So x is going to be the copy of the data that we're doing the pre-processing on. So we have a mixed column types here. We have some integers, some I don't think we have no floats, but we have integer, and all of the integer columns except for ID are count columns, or some sort of numeric continuous ranged column. So there are no categorical columns being encoded as integers. We can see that. Alright, so actually, I do want to make sure. It's yeah, I think the discount is numeric. Does it say here? It doesn't really say. Discount offered. I don't know if these are code or discount codes, or if they're like the amount of discount. The fact that it is distributed like this, with most as being small discounts and some being high, makes me think that this is the amount of discount that's being offered. So we're just going to assume that that is continuous, and all of our categoricals are encoded as strings. So we're going to have to do some categorical encoding to convert them to numeric. And I guess the first thing to do is let's drop the ID column. Since it doesn't contain any useful information for making predictions, since it's a unique value for every single example. So df equals df.drop ID from axis 1. Alright, next will be to check how many unique values are in each of our categorical columns. So we'll make a dictionary that will map the column name to the number of unique values in that column. We can get that by taking the length of x subcolumn dot unique, so the number of unique values, and we're going to do that for every column in x.select dtypes object dot columns. So we're just getting the column names from the object columns like this. Alright, and we have 5, 3, 3, and 2. So we have one binary feature, which is gender. That means it has 2 unique values. And easy to encode that, we just send 1 to 0, 1 to 1. One of the values to 0, one of the values to 1. And then the other categoricals are nominal, which means they have more than 2 values, and their values don't take any specific ordering. So one-hot encoding is how we will address these columns. So let's do the binary encoding. This is very simple. We just take the column, which is gender, and we call the replace function on it. And here we can specify a mapping as a dictionary that we'd like. So let's just send f to 0 and m to 1. However, I'll point out it does not matter which you choose. And then let's save the result of this back into the gender column when we're finished. Alright, now we'll do the one-hot encoding. And we're going to create a function for this, which is called one-hot encode. And this is going to take in a data frame and the column that we'd like to encode. We'll start by creating a copy of the data frame, and then we'll go ahead and return the data frame when we're all done. For this, we're going to use the pandas.getDummies function, which takes in a column, or a panda series. So let's pass in the, product importance. Let's pass that in here. Alright, so we can see the importance here. And you might be saying, oh, this is probably an ordinal feature because there's ordering of values here. But it's not so clear the spacing that we would assign to these values. Low, medium, and high, although they do take an ordering, they're not necessarily spaced evenly. If we give them 0, 1, and 2, we don't know that that's very accurate. So it's usually better in this case if you don't know the specific spacing to encode them as one hot. But you can definitely try it out and see which works better. So this is what one-hot encoding is. So you just get a 1 for whatever the original value was. So here you can see we have low, 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 medium, and so we have 1, 1, 1, 1 in those columns. So we can also include a prefix. Let's call it importance. Now I'll just put importance at the beginning, and we know this way where these columns are originally coming from. So in here, I want to take the column we pass in and create some dummies for it. So we're going to create dummies using pandas.getDummies. And we're going to do it for df subcolumn. And we'll specify the prefix to be the same as the column name. Then we'll just take those dummy columns and put them onto the original data frame. So df equals pandas.concat df and dummies. And we want them side by side, so axis 1. Alright, and then we'll drop the original column that we created the dummies from. So df equals df.drop, column, axis 1. Alright, that's it. So now in our one-hot encoding, we want to perform this function. We want to use this function on all of these. So if we look at this now, gender should be, actually, okay, let's run this. And you see gender is now encoded as 0s and 1s. And you see it's gone from the list. So if we just get the keys of this dictionary, then I can just copy this list of columns and paste that in here and say for every column in that list, then we're going to use our function one-hot encode on df where the column is given by column. Alright, and you can see we now have those one-hot columns on the end of our data frame, so we have all of the data in numeric form. So now we want to split and scale the data. So we'll split df into x and y. Y is what we're trying to predict, and the name of the prediction column is reached on time y.n, like that. And then x is going to be all the rest of the data, so we'll drop that column and save that in x. Then we'll do our train test split. So this is, we're going to send 70% of the data to the test, to the train set, and the other 30% to the test set. So we're going to get 4 new sets of data, which will be xtrain, xtest, ytrain, and ytest. And we're going to use the train test split function from sklearn for this. We just pass in x and y, specify a train size, 70%. We'll keep shuffle equals true on, and we'll include a random state since we're shuffling the data before making the split, so we can reproduce the results. Alright, then we'll scale x. So we're going to create a new scalar object, which is a standard scalar. And the point of scaling is to give all the columns the same range of values. The standard scalar will do a shift and scale to each column so that every column has a mean of 0 and a variance of 1. So we'll fit the scalar only to the train set, because we want to pretend we don't have access to the test set when we're doing the scaling. And then we'll transform xtrain using scalar.transform. xtrain. Now, this actually returns a numpy array, the scalar.transform function. So let's turn it back into a data frame afterwards with pandas.dataframe. And I'll include the indices to be the same as they were before, and the column names to be the same as they were before. Alright, and I'll do exactly the same thing for xtest. So I'm just changing these to xtest. And let's return these 4 sets of data. And we'll get them back down here. And we can take a look at xtrain. Alright, and you can see the data has been scaled. All the columns take a similar range of values. Alright, and we're ready to feed this into our model. Just note that a y-train contains our labels of zeros and ones. Alright, so we'll train. So we're going to use a whole bunch of models, as I showed you. Here they are. I've just put them into a dictionary where we are mapping the name of the model to the instance of the model. And this is nice because it allows us to iterate through from name and model in models.items. So using .items, we can return the key value pairs as tuples, so we can iterate through 2 at a time like this. And then we'll call model.fit on xtrain ytrain, and print out a little confirmation message that says that the model was trained. Alright, there we go. Now all that's left to do is get the results. For this, we can again iterate through for name and model in models.items, and we'll print out the name of the model followed by the accuracy value for that model, which is we'll display it to 2 decimal places as a percentage, and we'll get that using model.score xtest ytest. So the score function, if you're using classification models, will return the accuracy value. We just pass in that test set and it'll give us the result. However, we're using a percentage, so I'm going to multiply this by 100. Alright, and there it is. So all our models are doing more or less the same, but it looks like our ensemble methods are doing slightly better than the others. For these, we're getting always 65 or above, whereas with our single models, we only had one which was 65. And the best one here seems to be gradient boosting with a 68%. Alright, so that will sum up to this video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.